Okay.
So I started recording and I'm gonna start sharing. Okay, so here, input section. So let me, I got this. I'm gonna copy my A matrix. So here is the A matrix. This is a short period. And I'll just adjust these. This is negative. And here, this is the second row. This is negative, and I'm done with my A matrix short period. B matrix short period, let's copy that. And please stop me. Please stop me if you have any question. This is my B matrix. What else? Maybe we need the U notes. It was 800 feet per second, I guess. And we're done with the input section. Let's start a new section, which is maybe main program. If we want to look at the eigenvalues, okay, so here is the eigenvalues of the A matrix. And we run, you simply get your eigenvalues, the eigenvalues of the short period mode. So these are lambdas of the short period mode. We don't like them because when we analyze them, the damping ratio was small last time. So we want to analyze a flight control system. So how we do that? Well, it's a very nice command. It's called place. No pole placement. So we really place the poles. Give me the A matrix, please. Give me the B matrix, please. And look at the help here. It's A and B and P. What's this last? P is the location, the desired locations of the pole. So I need something here before that is the desired P desired. So these were what? They were the poles. I mean, I had the desired characteristic equation, which is, and if you have the desired characteristic equations, these are the roots. So there is the command roots of, give me the coefficients of the polynomial. It's 1 times s squared, 2 zeta omega n, 2 zeta desired times omega n desired, right? And omega n squared. So we need to define these. So let's define, zeta desired was given from the flying qualities table. It was 0.825, if I remember correctly. Omega n desired, we said we're going to maintain the same omega n as the short period. So omega n desired is simply the same as here. How to get the omega n from the poles? Well, it's the real square plus imaginary square. So it's the absolute value of one of these lambdas. So say the first one. They are both have the same thing. It's complex conjugate. Please stop me if you have any question. So this is my desired. This is coming from the flying qualities. And this is same as loop. Now I got the desired poles. This is the pole placement command. So now I'm going to have this P desired as is. What you will get out of this is the gains. So let's run. These are the gains. One was negative 0.023 and one is 23. And these are really the gains that we got last time. Okay. So, oh, there is something here. There is these negatives I did not provide. I'm sorry. These were negative numbers. Yeah, here. This is why the gains were flipped. 0.023 and negative 23. Here are the gains. Fine. So you got the gains. Then let's do some simulation. Okay, let's do some simulation. The command that I like for simulation, it's called LSM. It takes what? It takes your system, my system. It takes the input. It takes the time. And it takes initial conditions. So let's define these and come and do here LSM. Please, if you have any questions, stop me. I'll upload this file, but we're just doing it together. What is my system? There is a command called state space. It takes the matrices of the state space and create, like you see here, A, B, C, and D, and create a system, a dynamical system. My A matrix is the A of the closed loop system. So let's get the A closed loop. This is A minus B times the gain, right? So this is my A closed loop. B of the closed loop is B as the open loop. So this is B short period. What are C and D? We did not talk about them before here. So let me give you short notes about that. In fact, the state space model, x dot equals ax plus b. This is the input. So these are the A and B. It's not only this equation. There is another equation, which is called y equals cx plus gu. So what is x? X is our state variables. So what is u? U is our input. So what's y? Y is our output. And you're free to define the output whatever you like. It does not matter. So this is just to define which variable you're more interested in. For example, is my x's are w and q, like this example, okay? And you can define your y, the output, to be the angle of attack, right? So please write this relation in this form and give me your C and D matrices. What do you mean? I mean that write y as some matrix times your states plus some matrix times your input, which was delta elevator in this case. Can you fill these matrices, please? Yes, if my y is the angle of attack alpha, how it is related to W, Q, and elevator? Well, in fact, it is 1 over U naught times W, 0 times Q, and 0 times delta elevator. So this is my C matrix, this is my D. These C and D are for defining a specific output Y. If you are interested in Q instead, then my C would be 0 and 1, right? Any question about that? So C and D is just a way to define what is the variable of interest to you, the output. Doesn't matter much, but so let's take this as the output. So my C is 1 over U naught and 0, and D is 0. So here is C is 1 over U naught and 0, and D is simply 0. So now I've completely defined my system. So the first entry here in the command of linear simulation, this does linear simulation or simulation of linear systems. Okay, so I defined my system. What else do you need for the simulation? I need the input. What input you're gonna give? It depends on what is the simulation you want to achieve. Let's do simulation for, say, 5 degrees elevator. So the input will be a 5 degree, so 5 times pi over 180 times 11. This is the 5 degrees elevator. And it has to be defined for all time. So let's define time first. So my time will be, say, linear space between 0 and 10 seconds. So if this is the case, then the input, I can have it as ones, right? It's a constant input for all times. So ones of the size of time, right? So I define the input, I define time, I just need to define my initial conditions. The disturbance. If you like to give it a disturbance, give it a disturbance here. If you like to operate with zero disturbance, it's up to you. So now this, you take three things out of that. You take the output, you take time back again, doesn't matter, and you take matrix that has your states. In particular, let's now do plotting. Let's plot, say, time and your y. This is the angle of attack. And let's multiply by 180 over pi. Okay, let's run, see if there are any errors. Did it go through? Yeah, here is the angle of attack. It's very small change, right? And if you want Q, so X, what's X now? Let's look at X. What's X? This is X, 2 columns versus time. So the first one is the first state, which is W versus time. The second one is the second state, which is Q versus time. So if I want to plot Q, for example, versus time, what do I do? Well, let's do here and create another figure. And do plot T and the second column of X. This is the second column of X, right? And let's run this. Here is Q versus time. Let's give, instead of this input, okay? I'm gonna give 0 inputs. So this is 0 actually. But I'm gonna give an initial disturbance. Initial disturbance, 5-degree angle of attack, okay? So I'm gonna give here 5-degree angle, so 5 times pi over 180, this is 5-degree angle of attack, but my first state is W, so I need to multiply by U naught. This is initial disturbance. I'm gonna simulate that. So this is here the disturbance, the 5 degrees that you get at the beginning, and it dies out after a while, okay? I need to check if my elevator in correcting for this motion did not exceed the limits. I need to retrieve my elevator. How can I retrieve my elevator? Any suggestion? How can I retrieve my elevator?
You change the value of D.
Change what?
The value of D.
The value of D affects the output. So this is the output equation, frankly speaking. This is the output equation, and this is what we call the state equation. If you want to retrieve your U, how are you going to retrieve my input, the elevator? How can I retrieve the elevator? In general, how can you, aside from MATLAB? MATLAB is just, we do it after the fact, after we know how to do it by hand. If I ask you, find your elevator deflection for this, during this excursion. And this is, remember, this is a feedback control, right? We're simulating the closed loop system. This is the closed loop system. So we're simulating the closed loop system. How can you retrieve your control input from a closed loop system?
Don't you take the negative of the gains times the
very good, the control law. Very good, your control law. So here, my control law was simply U is negative the gains times the states. K as a row, and K is really, here is a row, here it is, times the state as a column, okay? Times the state as a column. So let's do it for loop, just to, for I equals 1 to length of T. For each time, here is my input at this time. It's the entire K matrix times the x's at that time. The x's, as you see here, so I need, at each time, I need the row corresponding to this thing, and I'm gonna transpose it. So here is the row corresponding to this thing, right? And I'm gonna transpose it. This gives you a scalar. The multiplication gives you a scalar. That's a row by a column. So I'm gonna take this row, make it as a column, multiply the k by that column, you get a scalar. This scalar is the amount of input. This is your delta elevator. And it's in radians, so maybe we can multiply by 180 over pi. So let's now plot T and delta elevator. Oh, this is T, it was time, right? Time or large T is the same. So let's have it as a new figure. Where is the third one? Didn't finish it. Oh, here. Okay. This is, yeah, it actually follows. So it starts with a large value because it was a large error. And then eventually, after you converge, it converged back. It shouldn't be the exact same value like we give a 5-degree disturbance, you start with a 5-degree elevator. This is just a coincidence. But at any rate, we need to look at this. Why? Because I need to make sure to simulate all possible combination of disturbances and make sure that my elevator deflection did not exceed the limits. Because if the required elevator exceeds the limit, what will happen in actual flight? It will not exceed the limit, right? Because there is a mechanical constraint on it. So what will happen? It will give, say, if you required here 30 degrees and the maximum was 25 degrees, then your servo will give only the 25, which means that you will not give the required elevator deflection for the good performance. So you will depart from the good flying qualities that you desired your flight controller for. And this is a consequence of a large gain. When you have large gain, it's not smart to have all the poles at -100, having your settling time in 0.01 second or 0.04 seconds. It's not smart. Why? Because you will not simply be able to achieve it. You can achieve it theoretically, only theoretically, but when you go and implement it, the required control action, the elevator, will be too large. So your servo will not provide it, and as a result, then you will not get this performance. Okay, let's give some labels here, and we're done with this. So this was, where are the plotting? Oh yeah, this is why. Here the plotting. So here, this was what? This was angle of attack. And this was, I think, Q. This was in degrees. This was in radians per second. And finally, this was the elevator deflection. All right. Any question about this? Super simple stuff. Fine. Let us now go here. Let's discuss the final. Let me okay, share screen. Sorry about that. Let's discuss the final. So as you guys know, part 1 is not there. So I'm going to start with lecture 8. Lecture 8 was really the equations of motion. right? So mass times acceleration plus the other part equal forces, X, Y, Z, and F gravity. And we had this issue of F gravity, so this is why we had lecture 9 about Euler angles. And if you recall, this was quite important. We had it as in a quiz, we had it in homework 5, and if you recall, there were 12 possible combinations, so I can ask you about any of these, right? So there is plenty of questions that I can ask here, and for sure we will. So this is a very important lecture that you need to take care of. Then we have lecture 10. After this lecture, we got the gravity, right? We got here, we have the gravity, fine. So after that, we had the 9 by 9 nonlinear equations of motion. The heart of any flight simulator. So we need to do analysis. So what's the first step? If you want to do analysis and you have nonlinear equations of motion, any suggestion?
Taylor series linearization about a point.
Linearize, very good. The first thing by an engineer is to linearize, and this is what we did in lecture 10, linearization. So by itself, I will not be quite adamant to ask you about linearization in the final, but it's quite a useful tool, and it was enabling for us. Why? Because really linearization and symmetry now led to the decoupling of this 9 by 9 into 2 sets, longitudinal and lateral. So the linearization led to decoupling. The linearization led to the appearance of too many terms, MQ, LP, NR, NP, you know, you name it, stability derivatives. So this is why we had lecture 11 on stability derivatives, how to derive them. And really, stability derivatives is a very important topic. So this is why, if I can ever ask you, I will. We did it on a quiz, we did it in homework 6, and expect a question in the final for sure. It's a very important topic, very important lecture, because the derivation of, and again, these are too many stability derivatives, but there are too many. And for each one of them, we have like wing, tail, blah, blah. So you can play all sort of games. So you cannot memorize things. You just need to really understand. And interestingly, if you understand how to derive stability derivatives, you understand flight mechanics. This is the heart of flight mechanics. How to derive LP for a wing or a horizontal tail, how to derive NP. And if you are okay with the questions that we had in the lecture and the homework was quite hard in this regard, and I have to admit it. So if you are comfortable with the level of the lecture, and if you got the level of the homework, then you're fine. Now we have a linear system, and we managed to derive expressions for these parameters. So our linear system is ready. So you need to do analysis. So this is why we had a review of linear systems. What is settling time, overshoot, its relations with eigenvalues, and all of this. And state feedback in particular, how to design a state feedback controller. So on its own, this is a pure control lecture. So I'm not going to ask questions about it on its own, but of course it will be within our course. So it's good to review it. The same for vibration. I'm not going to ask questions about vibrations. Then lecture 14 and lecture 15, these were about the longitudinal modes, right? Which are how many modes, by the way?
2.
2, the long period and short period mode. Lecture 15 was about the lateral flight dynamics. These are 3 modes. Dutch roll is the most important. We have the rolling mode, we have the spiral mode. Then lecture 16 was fine. We have now the airplane flight mechanics, which is started with nonlinear equations of motion, 9 by 9. Now it's decoupled into 5 systems. Each one is simple enough. If we just, and we have a very powerful theory that can do control for these systems. If we just know what do we really want to achieve, we're done. So this lecture 16 was about that, in particular, flying qualities. What is a good airplane? What's a bad? How can you determine if this airplane will fly well or not? Or what is the criterion to design a good flying airplane? So lecture 17 really culminates all that. Stability augmentation and control augmentation, autopilot design kind of thing, or flight control design.